Hello, everyone. It is great to be back in Vancouver. I was here about 3 months ago, actually, to the day, and it was very rainy and dreary. I think we got maybe a couple hours of sunshine when I was here. And so yesterday when we were flying in, we hit right at golden hour, and so I got to see the sun setting over the city and the mountains, and it was just beautiful. So thank you again for welcoming me into your city once again. So without further ado, the AST and me. So a little bit about me. My name's Emily Morehouse. I am the Director of Engineering at a company called Cuddlesoft. So Cuddlesoft is a digital product development company where I get to work on anything from CI/CD pipelines and system architectures to web and mobile development, UX, and IoT. So I'm actually going to preface this talk with a slight note. The language that I use for many of the examples in this talk is Python, but the same concepts apply for many, many other languages. The tools that I use also have similar counterparts in other languages, so please don't tune out just because you don't know a whole lot of Python. So what we're going to cover is a 10,000-foot view of how you get from source code to execution of a piece of Python code, how to interact and inspect each step of that process, current Python optimizations in the compilation process, and practical applications of how you can use ASTs both inside and outside of the Python world. So the question is, should you care about language internals? And my answer is yes. Yes, you absolutely should. So let's take a slight peek under Python's hood. We're going to start our journey from source code to execution to build an understanding of the broad steps that it takes to compile a piece of code. So the first question is Python interpreted or compiled?
Yes.
And yes, that is exactly the right answer. It is both. So Python has a compiler that generates bytecode, and then an interpreter that makes sense of that bytecode in order to execute your code. So one of the ways in which Python is dynamic is that the same piece of bytecode doesn't necessarily always have the same outcome. So let's zoom in a little bit to see a more detailed view of what this process looks like. So you start with your source code. You parse your source code into a parse tree. And now parse trees are a little bit more detailed than what we actually want. You'll see a diagram of what this looks like in a moment. So we transform our parse tree into an abstract syntax tree. Another transformation into a control flow graph, or a CFG, which is essentially a directed graph that models the flow of a program. From here, we can now emit our bytecode and finally execute it to get our final output. Now, this is quite the process with some very intricate steps, so we're going to focus on just a few key parts of this process, namely our source code, the AST, and our bytecode. So let's back up a couple of steps. So what actually is an abstract syntax tree? So an abstract syntax tree is a tree that represents the structure of your source code. But hold on, what is a tree? Because this is a tree, and this is also a tree. So trees have one single root, the top node. Nodes can branch off to other nodes. But each node, except for the root, has a single unique parent. So when we read this, we start at the top node, and we work our way down as far as we can on the first branch before we start on the next side, performing a depth-first traversal. So let's take a look at the difference between our two types of trees. So we're going to start off with a very simple arithmetic code example where we have 1 plus 2 in parentheses times 3. So if we look at the parse tree for this, this is essentially going to be a one-to-one mapping of our source code based on our language and grammar in tree form. And so one of the things that we're not covering today is tokenization, so taking that code and figuring out which pieces of it we're going to divide it up into. But you can see in this graph that we can take it into different factors, expressions, and terms, and we're going to separate it out into parentheses, numbers, and different symbols. And so on the right, we now have our AST for the same piece of code. So you can see that we've left behind all of the kind of syntactical specifics, so we can instead focus on how the underlying objects are structured and the true meaning of our code. And so we as humans who have learned the order of operations know that when we evaluate this expression, we want to evaluate 1 plus 2 before we multiply that result times 3. So you can see here in our tree, as we follow our depth first traversal, we're still going to perform 1 plus 2 before we get to the multiplication times 3. So let's dig in. Now that we have an understanding of the life cycle of a piece of Python code, let's see how we can actually interact with this process. So these are, again, Python specific. So some of the primary tools that I like to use to do this is a couple of built-in modules in the Python language itself. So there is an AST module that you can use to interact with AST. There is the dis module, which you can use to disassemble bytecode into a few different things, which we'll see in a minute. And then there's also a few secondary libraries that I like to use, one of which is called Aster, another called Meta, and another one called CodeGen. So not all of these fully work with Python 3, but for the most part, they do. All right, so we're going to start with a very simple piece of Python code, a print statement that takes a string as an argument. So we have our source code assigned to a variable. We can now generate the AST using ast.parse. So we specify the source as well as the mode that we want to process our code in. So we want to evaluate this code. So now we have a tree generated from our code stored as an ast.expression. But this isn't really very useful to us quite yet. So we can actually dump this AST. But it doesn't give us anything that's extremely legible right off the bat. If we look closely at this, we can kind of see that we have a function called print. It's being passed in as a string. There's an ID assigned to it. We have some context around it. We have our string that we passed into the function. And then we also have some optional keywords that we didn't actually specify here. So we'll push forward. We can now take this AST and compile it into bytecode by calling compile. So this is awesome. We now have a code object. So if you don't know anything about Python, one of the really interesting things about it is that everything in Python is actually an object. So as you're compiling your code, everything gets compiled into something called a code object. So we can take a peek inside this code object to see a bunch of different things. But most importantly, we can actually see our raw bytecode. So I don't know about you, but I can't actually read this. If you can, that's very impressive. But what we can do is we can actually tell it to evaluate this bytecode that we have compiled. You can see that it prints out, "May the force be with you." So let's take a closer look at that bytecode, since it wasn't very readable. We can actually force the interpreter to show us the bytecode that's more legible to humans. So somewhere along the lines, our compiler actually makes sense of these bytes. It would actually take us a lot of time for us to do this manually ourselves. There's actually a giant switch statement in Python that handles all of your opcodes. So somewhere along the lines, these are all defined. There's a giant switch statement, and you can go through and find what does 101 do, what does 100 do, what does 131 do, etc. But like I said, this is really cumbersome to do as a human. So we can now use our disassembler module to help us out. So what we can see now is a pretty clear description of what's actually going on when this code is run. So we can see that we are loading up our function, loading up our string that we passed into it, and then executing it. So this is pretty simple with this example. But what does all of this actually look like in our abstract tree form? So here is the AST and the disassembled bytecode for our print statement side by side. So this is actually pretty readable at this point. We can see that there is a single statement, so we don't need any nesting in our AST. We'll call load name for our print function, load const for our string that we passed in, and then we simply execute and return. So in this example, it's simple enough, right? But as we continue to add code, even just a simple if statement or a variable declaration, we can see that our examples get progressively more and more complex. But our AST still helps us visualize the path that our code takes. However, a caveat to all of this is that what we wind up with in our AST, or bytecode, is not necessarily going to actually match our source code one-to-one. There are certain shortcuts that our compiler takes when creating our bytecode. So let's actually go ahead and take a look at what sorts of compiler optimizations are affecting our bytecode. So Python's compiler is actually purposefully very simple, or at least as simple as it can be. The best way to optimize Python is actually to completely replace the implementation of Python itself, which is actually CPython, and switch it out for another interpreter. And people love doing this, so there's a ton, like Python, Jython, Cython, IronPython, Stackless Python, MicroPython that's built to run on microcontrollers. There's a bunch of different options for this. So Python, the language definition itself, can actually be completely independent of the implementation used to bring the language to life. So one of the optimizations that does exist in Python is called the Peephole Optimizer. We'll get into exactly what that is. And then otherwise, there's really very few AST optimizations besides something called constant folding in Python. But if you're a language nerd and you're really interested in language implementations, this is a really great place to dive in to see the different ways in which languages handle optimizing. So let's talk about peephole optimizations. The way that I like to think about peephole optimizations is looking around without moving your head. So really kind of using your peripheral vision to see what it is directly around you. So a simple example of that is if we have x equals 1 and y equals x plus 2. So most of us in this room, I hope all of us in this room, or anybody with middle school algebra can look at this and go, okay, x equals 1. That means that I can simplify this into y equals 1 plus 2. So this is actually an optimization that a lot of compilers will use. Another one that I find really interesting is that essentially the Peephole Optimizer will take excessive or redundant logic and simplify it for you. So if you do something like not A, not in B, the compiler actually sees that and goes, okay, no, this is just A and B. I can do a lot less work on this than I actually need to. And let's talk about constant folding. So constant folding is essentially evaluating constant expressions at compile time instead of at runtime. So essentially what you can do is take a constant expression that are simple literals, such as the integer literal 2, but they also might be variables that are defined constantly at other points in your function. So not all languages do this, and sometimes they don't actually evaluate these expressions into constants. But a very simple example of this is taking something like a equals 2 times 3 and simplifying that into just a equals 6. So now let's talk about how the AST actually affects your code. So we now know that bytecode is created using an AST. And so for Python, bytecode is actually stored in PyC files. So Python actually uses something called a magic number to determine when your code is changed and when that bytecode needs to be regenerated. So if you're making a change in one file, it doesn't actually have to regenerate the bytecode across the board for all of your files. But like I mentioned, you get very, very micro speedups. To get major speedups, you have to completely change out your implementation. So because Python is just a specification for the language, it can be implemented in many different ways. But when you make the choice to switch out your interpreter for a faster one, you're always going to have to kind of take a step back and evaluate what you're losing by switching out as well. So a lot of times the language won't be fully compatible in a different interpreter. But if you need the speed but you want to write in a language that's as friendly as Python, that is still an option. So some practical applications of having a little bit of knowledge about ASTs. yeah, you can kind of improve and speed up your code. I think this is more applicable in languages outside of Python because Python's AST optimizations are so simple. It can help you debug errors if you understand the traceback and the flow of your code a little bit better. You can do really fun things like changing the Python grammar and playing around with a new operator that you want to add or a new language function. Something that I find really, really interesting is something called round tripping. And so this is really great when you are refactoring code. And so you can actually compare your AST from before you refactored your code and after you refactored it to make sure that you're not messing up the meaning of your code when you do something as simple as a replacement to change all of your tabs to spaces across your file. Or a lot of times in something like JavaScript, if you're going through and adding or removing semicolons or commas, you can compare your AST and make sure that that didn't actually mess up the implementation of your code. Another really fun one is code generators. So a lot of Python's compiler itself is actually generated code. So that's something that is really fun to kind of explore what you can do to set a template and then actually generate a lot of your code, whether that is something like generating a new modular template for a website or generating new templates for new server deployment. Again, we mentioned alternative interpreters. You definitely have to have a really good knowledge of ASTs and how they work and how Python's grammar is meant to function. And so the interesting thing is you can make an interpreter to go from Python to Python itself or from Python to other languages. So one of the really interesting projects that I love is called PyB. It's so that you can basically write Python code that gets transpiled into native Android or iOS code. Or something like Jinja or other templating engines. All of these rely on ASTs. So applications outside of Python. Code analysis. Anytime that you are doing any sort of static analysis or code linting on your code, whether that's in a text editor or a grunt command or gulp command that you're running, all of this is using an AST. Code transformations, like I mentioned, but ones outside of Python that are very popular are something like PostCSS, something like Babel that allows you to take ESNext features and compile them back down to ESNow so they can be run in all browsers. Different migrations, so if you're going from Python 2 to 3, you can utilize an AST for that. And then React Native, which is very similar to something like PyB, where you're writing code that gets transpiled down into something that can run on other devices. So this is a list of my resources. This is not for your eyes now. This is for your eyes later if you're interested. There's a lot of information here on ASTs, on Python's compilation process, on tools that you can use to create or analyze ASTs. And that is it. This talk is hosted on my GitHub, and the source code and all of my experimentation scripts and code that I ran is all in there as well. So I think I've got a few minutes left if anybody has any questions.